Here, let's take a look at a graph, and we're going to determine what the domain and range is of this graph. This is a common exercise that we're given in mathematics because in mathematics, it's often useful to look at the result of an entire structure over a variety of inputs. So we look at it in terms of a picture, because with our eyes, we can absorb so much more information than we can if we just go number by number. So let's talk about this in terms of domain and range. First, as a little bit of a refresh, is this the graph of a function? Because keep in mind, not all graphs are functions. Functions is an elite title given to a relationship that takes one input to one output, which means you have to be unambiguous with any question that you ask and the resulting answer. So let's take a look. If I asked a question of the number 1, where does this graph take me? Well, I would input x as my 1, and I would go up until I got to the graph, and then there I would reach a height, and that height would represent the answer I got from this structure. So 1, 2, 3. So sure enough, this looks like it is at least a function at the number 1. And if we do this all the way across, we'll see that sure enough, this is going to be true everywhere we have. In fact, this passes what we call the vertical line test. The vertical line test is a visual test we can give to a graph to say, at every single input x, am I going to have at only one possible answer? And even if we go over here at some x values that are off the graph, there still is no ambiguity. There's just no answer. These are parts of our domain that just don't have a good output. So, okay, now that we've kind of introduced the idea of this being a function and we've kind of briefly alluded to the domain, let's talk about that. Domain is going to be the collection of all possible questions or inputs that we could use this picture to help us with. So, for example, 1 is in our domain because I could use 1 to go up to the graph and get the answer related for 1. The answer would be 3. 2 would also be a part of our domain, and 3 would be a part of our domain. So we could begin describing this entire thing as saying, well, 1 is in our domain, and 2 is in our domain, and 3 is in our domain. But this is where we need to be careful that we don't start getting a little bit lazy with our interpretation of this picture. Because after all, 1/2 is also in this domain, and 1/3, and the decimal 0.634, and a variety of other things, square root of 2. So do we really want to go through trying to list all of the infinite number of different numbers that are in our domain? Okay, we'll be creative. We'll look at this in a different way. Well, this number works, and this number works, and this number works, and all the numbers in between here work, and all the numbers up to here work, and I think even this number works because it has a height of 0, and we could go all the way back to this answer because it has a graph right above it. So really what we're talking about is something described as an interval. An interval is something that starts and ends, but in between the starting and ending points, it is continuous. It is uninterrupted. So we could actually describe this using words as saying it's the interval starting after 0 until, what would that be? 4, 5, 6, 7, until 7. So let's reflect on that. It's an interval that starts after 0. Oh, but that's not entirely correct because it actually starts at 0. So we're going to need to correct that a little bit. It doesn't start after, it starts at 0 and until 7. Okay, so it includes 7. That's true. When we talk about this using shorthand, we'll often use brackets and eventually parentheses to describe this situation. To say that it starts at 0, we'll say 0 is kind of our hard start. And we'll use a bracket to show that 0 is part of this conversation. And it'll go all the way up until the number 7. And we'll close that one off as a bracket as well. So now what this is a shorthand that says our domain is an interval beginning at 0 and continuing all the way up to and including the number 7. Okay. So that's actually a nice quick way of doing it. We don't need to list numbers. We don't need to rely on full sentences. We can use shorthand notation of bracket 0 to 7 bracket as being a notation to say that we are starting at some place, ending at some place, and continuous in between. What about for the range? Let's look at the range. So we got the range would be this similar shadow that's kind of being cast over here on the y values, because we're looking for all the possible heights that we could have as a result of this function. And sure enough, this height of 4 up here is a valid height. Is the height of 3 a valid height? Yep. Here's a place on the graph where I have that height, and over here as well. What about at 0? This is a place where I have that height, and I go all the way down until it looks like at a height of -2. So in between -2 and all the way up until we get to +4, these are all heights or outputs of our function. So we could describe that again using interval notation. We're going to start at a most negative value of -2 and continue all the way until a most positive value of +4. And that's how we would describe our domain and our range using what's called interval notation. Let's look at the domain and range of a few other graphs. So for example, let's take a look at this one here. This 2x plus 1 is going to be the equation of a line. And how do we know this? Well, perhaps we've forgotten. We can go back to drawing our table of values and use that as a way to help us with plotting out exactly what this function is. So we'll start with a variety of questions we can ask, which is our x, and then that's going to get us out the results of the function f, the story of steps, which we call f. And that function, of course, is 2x plus 1. So if we're going to be replacing x with a variety of other situations, like let's try the number 1, over here we're going to be replacing x with that 1. We're looking now at f of 1. That's a shorthand for saying the function called f at the value of 1, but we'll just say f of 1. Okay, if we're replacing x, let's replace it everywhere. So we have a consistent statement. That'd be 2 times 1 plus 1, and that's going to be equal to 3. So we could go up here, we could plot that at a value of 1. We're going to go up to a height of 3, 1, 2, 3, and make a point right here. And we could do another one. We could do it at 0. So f of 0, if we plugged in f of 0, would be 2 times 0 plus 1, and that would be equal to 1. So at 0, at an x value of 0, we go up to a height of 1. And if you do this more and more, you'll see that what you're actually going to get is a line. And so I'll just sketch that in right here. So that's going to be our sketch for the function. And of course, this isn't just values at 0 and 1, but we're doing this line as a way of kind of extending that we could do the same logic to 1/2, or to the square root of 2, or to negative numbers, that they're going to plug in here and get points as well. So what's the domain and range of this graph that we've created? Well, our domain is going to be all of the valid inputs we could put into here. In other words, all of the numbers that we could effectively multiply by 2, and then the result of which we could add 1 on top of. So let me ask you, is there a number that you cannot multiply by 2? Well, maybe a quick checklist. Can we multiply positive numbers by 2? Yes. Can we multiply 0 by 2? Yes. Can we multiply square roots of numbers by 2? Sure, it's just not pretty. Fractions, we can do that. Negatives, we can do negatives. So yeah, there's everything we can multiply by 2, no problems. That's just going to give us another number. And then with that other number, I'm going to add 1 to it. I'm going to get another number. So that means that my domain is all real numbers. It's every number that I've just explored. We didn't get into complex numbers or imaginary numbers, anything like that. But so we'll just say all real numbers for now. So sure enough, all real numbers. Now we talked about before how to describe this with interval notation, because after all, if I was to look at all of these x values that have a valid output, even this one, if I go down far enough, is going to effectively hit the graph, and this one here. So all of these x values will be valid inputs for my graph. So that means I could describe this as an interval. It's an unbroken stretch of numbers that all work. But I don't have a lowest value that works. So where does this interval start? Many of you would say that it starts backwards at negative infinity. And okay, let's explore that for a moment. If we say that it works backwards at negative infinity, let's clear out some space here so we can move this down. Then we'll put in here that we have negative infinity being the starting point. That'll go all the way until what? I guess positive infinity, because there isn't a highest number that's not going to work here. So I guess this will go all the way until positive infinity, and then we'll write it in the same interval notation we knew from before. We'll do some brackets. But that means that I'm starting at negative infinity and going all the way until infinity. As a quick aside, infinity is not a number, which means that this doesn't actually make sense the way that we just said it. How can you start at something that's not a number? I mean, after all, try to go out and find it. Try to count up to it or down to it. If you don't believe me on that one, okay, let's try it over here. Let's take a quick side note. And let's explore. Is it a number? Many people would say yes. Spoilers, it's not. Let's do a side note. Is infinity a number? Well, what do we know about numbers? Numbers have to increase if I add the number 1 to them. For example, 1 is a number, and if I add 1 to it, I get to the number 2. And even square root of 2 is a number, because if I add 1 to it, I'm going to get 1 bigger than the square root of 2. Negatives, I would add 1 to it, and I would get more positive from that. So, okay, the condition that we have for numbers is that numbers grow when you add 1. But infinity is the biggest number, so what happens here? What would infinity plus 1 have to be? Well, if it's the biggest, and we've taken one step beyond the biggest, that means we're still at the biggest, there's nothing bigger, so that must mean that I get infinity. But if I add 1 to numbers, they have to grow, and this one didn't work. In fact, a better way of showing that is that if I then subtracted infinity from both sides, what do we get? We get that 1 is equal to 0. So this is where the difficulty comes when you're talking about having a biggest number or a smallest number. Infinity and negative infinity, they're not numbers. They're ideas, they're stories, they're concepts, they're models, they're symbols. They're not numbers, because if you treat them like numbers, you'll get into a conflict where either you have to decide that numbers don't grow when you add 1 to them, or 1 is equal to 0. There's really no other way of getting around it. So this is where we want to be very careful when we're coming back and looking at some of the work that we're doing with these brackets and parentheses. We cannot say things start at negative infinity and that they end at positive infinity. We can, however, use this as a placeholder, as a symbol, to show that there isn't anything better to go there. But instead of using a bracket, we'll use a parenthesis. A parenthesis says that there isn't something hard and fast I can grab onto as the start of this interval, but there isn't right after the smallest number, the smallest negative, the biggest negative, like right after that, sure, everything else works out just fine. And so this is why we will use parentheses. It's not to talk about at, but to talk about after. So quickly, the range for this one, if we go again and we look at where's all the shadow that kind of gets cast on this y-axis now, all of these are valid heights that the function has. So again, this is going to be all real numbers, or we could describe it as saying negative infinity to infinity. Okay? Now let's look over here at our example of a parabola. This is g of x equals x squared. You could type this into a graphing calculator, or you could do the same table exploration. Hopefully you have seen this somewhere before, and if not, it's going to look something a little bit like this. It's going to be a parabola or a U shape that graphs up like this. And so let's describe the domain and the range for this one. For the domain, we would have, well, let's look at where that shadow's kind of being cast. Let's look at all those valid inputs. Is this a input that works out just fine? You could go up to the graph and it would hit it, so it must be. This is a good x value, another good x value. In fact, all of these, again, are valid x values. So the domain, again, would be all real numbers. Everything starting after negative infinity, because you can't include it, up until infinity, because you can't include it. What about for the range? For the range, we'd be looking at all the heights that work with this situation, and the heights only show up here. So we would need to describe this in terms of saying, okay, well, it looks like it starts at 0, it goes up until it never stops, and then since we can't include infinity, we'll put a parenthesis. Is there ever a height of 0 with this picture? Yes, this is a height of 0 right here, so we will include that with a bracket. So this is what we would call a half-closed or half-open interval. These are open intervals because there isn't a place for us to close them off at. This is a half-open, half-closed interval because there is a place for us to close it off at only one end. All right, what about this next one? This is the same graph, h of x equals x squared, so we could start by drawing that parabola. Just a simple sketch will do for this exercise. And then we're looking for x values that are bigger than 0. So let's take a moment and let's look for where those at. This is an x value of 0, but is x equals 0 bigger than 0? In other words, is 0 bigger than 0? No. So we'll put an open circle here, and then all of these work out just fine, so these will be fine. Nothing over here works out well, so we're going to have to get rid of it. Let's erase everything from over here. And this will become our new picture, is showing how this parabola is going to start off not at 0, but right after it. So open circles in our graph are a nice way of being able to show that I want to convey an idea of something that's happening near there, but I can't talk about at there. It doesn't actually work. We could, of course, have just tried to erase it, but look at the story that this kind of conveys. This conveys that there is not an x value of a half that works, because 1/2, there's nothing above it. Even though there's nothing wrong with 1/2, it's definitely bigger than 0. So we would have to include a half, and then we'd have to creep into a quarter and then creep into an eighth. So really we're left with one and only one option. Let's just put a circle around the absence and everything else will be included. So what would be the domain for here? We already talked about it. We can only put in x values that are bigger than 0. So we'll talk about 0 as being a starting point for our interval. We'll go all the way until we don't stop. Can I include 0? I cannot. 0 is not bigger than itself, so we'll put a parenthesis. Can I include infinity? I cannot. Infinity is not a number, so we'll put a parenthesis. For the range, similar to what we had on the left-hand side, it looks like we would again start at 0 and go all the way up. But different from what we had before is that this would start after 0, because the height of 0 doesn't exist. There's an open hole there. So we will use a parenthesis to show that it happens with heights that are just a little bit bigger. We'll use a parenthesis to show that after 0, until it doesn't stop, is part of the range. All right, what about this last one? If you were to graph this out again with a graphing calculator, or if you know the quick shortcuts to draw it, this is going to be a graph that starts here and goes up as a parabola, but a parabola turned sideways. So what could be the domain? I'm going to leave this one mostly for you, but again, you're looking for where that shadow is cast, and you're trying to make sure that you don't have any situation of holes or places where the graph doesn't exist. So everything that I've shaded in here would be a valid part of the domain. See if you can draw that using your interval notation. What about for the range? Well, for the range, you're going to be looking for all the possible heights. So you're looking for the shadow that's cast on the y-axis where all of our heights are included. And sure enough, even the height of 0 is represented. So everything from 0, including 0, and up to the positive never stopping would be part of our range. And this is how you can explore the domain and the range from graphs. Graphs, after all, are functions made whole and visual, so we can now see that these structures right here of 2x plus 1, x squared with conditions, and the square root of x plus 2 have some places where we can plug numbers in, and sometimes where we won't get answers out.